Welcome to our presentation, Turbocharge Spark with Xilinx, Bigstream, and Samsung SmartSSD. My name is Sung Kim. I'm Senior Director of Data Center Systems Architecture team at Xilinx. I invited Steve Tui, VP of Marketing from Bigstream Solutions. Today's agenda is shown below. Introduction of computational storage and SmartSSD. And then we'll talk about what is the Spark acceleration, how it gets accelerated, what's the performance result, and followed by SmartSSD technical details. And then we'll conclude it with a brief TCO analysis. I'd like to briefly talk about industry around the computational storage first. There has been tremendous momentum within the standard bodies to support a common interface to computational storage. SNIA's Compute Memory and Storage Initiative is driving to develop common use cases and terminologies, and then also driving alliance to standardized interface. At the same time, the computational storage product have hit the market with the growing customer demand. In fact, we are happy to announce that the SmartSSD, a joint solution from Xilinx and Samsung, have passed its qualification requirement and made it available as a mass market computational storage drive. I will talk about what SmartSSD is, and then how it operates, and what kind of acceleration can be done in the later section of presentation. Before we delve into how Spark acceleration works, I'd like to introduce what the common use cases are for SmartSSD, and then what the key value that each use case can provide. The first use case is a transparent compression. A SmartSSD can provide compression and decompression functions using the acceleration logic inside SmartSSD. And then you can provide a lower storage cost. And in other words, a more storage capacity for the given dollar amount. And the second use case is a video file transcoding. We also call this faster than a real-time video transcoding. By utilizing video encode logic in the SmartSSD, you can write video files to the SSD directly after encoding video file without sending that actual video file to x86. This can increase the video transcoding performance by offloading compute-heavy the video encoding process from x86. And then you can reduce the latency involved in data exchange over PCI interface by enabling peer-to-peer technology. Another use case is a search in storage. The typical use case is a cybersecurity. Terabyte of the log data stored in the storage, SSD in this case, can be scanned by the acceleration logic in the SmartSSD. And then it returns only the data of interest back to the host or the applications. And then last but not least, today's focus is big data analytic. And then this specific use case is based on Bigstream's software and then hardware acceleration technology. They have implemented FPGA-based middleware to accelerate Apache Spark on SmartSSD platform without user code changes. Here, I'd like to hand it over to Steve, who can give you details around Bigstream Spark acceleration solutions.
Thanks, Song. Thank you to Xilinx for the partnership and including us in this talk. Thanks to Databricks for hosting the Data and AI Summit. As Song said, my name is Steve Tui, and I'm representing Bigstream here today. I want to talk a bit about what Bigstream offers in terms of being pioneers in big data acceleration, and also talk a little more about what we mean by that. Overall, there's excitement in this space of acceleration for Apache Spark, for big data platforms overall. Let's talk a little bit about what that means and how it's relevant to the audience at Data and AI Summit. Bigstream has been at this for about 5 years, and our focus is Apache Spark. So we have a platform that will cover other platforms beyond Spark, but today the focus is Spark. And what we really focus on is ensuring that the Spark user has zero code change. It's seamless in their usage of running Spark jobs with Bigstream. And basically, at our core is making Spark jobs run faster. And we have a product in the market today that includes both software-driven acceleration as well as hardware-driven acceleration. And we're agnostic to cloud or on-premises deployments. So I want to talk both about what acceleration is and what it isn't. Spark is inherently fast, people will tell us. So what do you mean you're accelerating this? Are you a different distribution than EMR or HD Insights or Databricks? No, we with acceleration build on top of the shoulders of the latest version of Spark and add acceleration to that. We'll also get the question, well, Spark is meant to scale up, scale out, bigger nodes, more nodes. So if I want to go twice as fast, can I just have twice as many nodes or nodes that are twice as powerful? Yes and no. So that is an expensive proposition, both in terms of money, doubling your spend, but also communication overhead. So our studies and others have illustrated that there are not linear scaling in terms of adding nodes. So this chart on the screen right now is a straight line. Just one test here shows as we add more nodes to a cluster with Spark alone, the performance gains are nowhere near linear. There's quite a fall off. Things keep getting faster, but nowhere near in proportion to the number of nodes being added. The other question that will come up is just, isn't acceleration, with Spark or any platform, can I just wait for the next version or upgrade? And that's where I get my acceleration. And we all really get excited about Data and AI Summit and learning about all the developments in Spark that are included in the other talks around the ease of use of the product, functionality, speed gains are certainly part of that. So you definitely will get the fastest instance on Spark 3.0 or 3.1 as you move forward. That again is not what we're talking about with acceleration. Bigstream and acceleration works on top of this. And taking each task or operation of a Spark workload or big data tools in general and identifying which of those can be accelerated. So I'm going to illustrate with an example here. So it's the pandemic. I'm at home, like millions of others. I decided, why not work in the backyard? We built a shed, and now we're finishing it. Right. And so for me, I thought, well, what's the project here? One person, myself, it's not that handy. Maybe it could take 2 full days to finish this. Some combination of putting up drywall, nailing that in, painting it, sanding it. There's a specific sequence to it. But this is my project plan. Now I said, I can get this done faster with a little help from my friends or family in a social distant some pandemic specific way. And if we have a plan and we organize this, we can make this run a lot faster. So this is sort of like going in a non-distributed fashion, pre-Spark, pre-Hadoop, shifting to Spark. So we're taking this 2-day process and now we're going to accomplish it in 6 hours. And the key, this is simplifying, but the key additions here is that we have an organized plan and we're distributing this across multiple workers. That's the analogy to Spark, which generates a data flow in the form of a physical plan, and then it incorporates the benefits of parallel computing, distributed computing, multiple nodes in a cluster. Okay, so acceleration, again, builds off what Spark has to offer. So it takes that plan and it takes those workers across a cluster. And what it does, again, is it examines specific operations and tasks in that plan and says, is there a way to make this faster? Is there a way to make this scan, this filter faster? Back to my shed, is there a way to do the painting a bit faster? Is there a way to do the nailing, right? And I make the analogy here to a paint sprayer or a nail gun, right? So the Spark is bringing together an organized team, whereas acceleration on top of that is taking individual tasks and operators and accelerates that. And so Song introduced the SmartSSD. That's one of several accelerators that Bigstream incorporates. And now we're going to deep dive a little into how that comes to life. To pull it back into the realm of the specific accelerators and Spark, and to summarize, there are several inherent limitations to the max you can get out of Spark that we've talked about a bit. So the diminishing returns to cluster scaling. Moore's law, basically, the CPU is dependent on for all the processing in most Spark jobs. And the CPU is great. We all use them all the time for just about everything. They are a generalist. But there are better tools for the job, for a specific job, for a scan, for a specific parallel processing, for machine learning. And we can incorporate those in with some help with tools like Bigstream. This final limit is, I've got there in the lower left, is Spark, like many applications, is written in a higher level language, so it's generalizable across all functions. But that leaves some efficiency on the table for specific operations that can be accelerated with software. So shifting over, this opens the door for the acceleration space, the space that Bigstream is a leader in, and that we're seeing a lot of excitement and action in. We are a middleware connecting the platforms like Spark with advanced computing options, be it hardware, be it software. It builds off of Spark, the physical plan, and we'll look at that a little more closely in a bit, targeting specific operations to accelerate. And core at this, especially on the hardware side, or in particular on the hardware side, is programmable hardware, field programmable gate arrays, SmartSSDs, and other forms of computational storage, GPUs, and even ASIC, which is kind of its own category in a way. And on the non-hardware side, Bigstream delivers acceleration with C++ accelerators. So to take it below that level of Java to, again, find specific tasks and operations that can be performed more effectively with Bigstream. The SmartSSD is one of the hardware implementations of acceleration. So all the hardware accelerators will examine the physical plan and go through task by task, operation by operation, examine that, Bigstream will examine that, and determine which of these will benefit from a software acceleration or whatever hardware acceleration is available in your cluster. And so a specific operation, it might determine the SmartSSD is going to run this faster than the CPU. So you're freeing up the CPU, sending less to it, so it becomes less of the bottleneck. That works with any of our accelerators. What's unique about the SmartSSD, though, is that it actually limits what gets to the CPU and reduces some of that traffic and overhead that we talked about before in terms of adding more nodes to a cluster. And I'm illustrating this below with two timelines. One, the first one is running without acceleration and without a SmartSSD. And so here you see data will move off of storage, off of an SSD as a transfer step. That's blue. In red, there is a filter and decompression that happens on the CPU, and then further SQL processes in that teal color. The SmartSSD not only accelerates the filter and decompression and accelerates the SQL processes, but it does that filter and decompression in storage on the SmartSSD. And so that red piece is shorter because it's doing it more effectively. But then the big piece is also that blue in the middle. It is a much smaller volume of data that makes its way to the CPU and therefore puts much less pressure on the overall cluster. Even that part is more efficient with the transfer. And then the SQL process at the tail end is also accelerated in a different format. So each of these three chunks are all shorter, but then the sequencing of these reduces that bandwidth and challenges there. The other key point I want to make here on the SmartSSD is some of the main computations that do get offloaded from the CPU by the SmartSSD are decompression and filtering, which we mentioned in that example, but projection, data format processing, and selected SQL operations as well. So let's take a look at some of the results that we have recently with the SmartSSD in a Spark cluster. These are across the 100 TPC-DS queries, so the decision support part of this. So these are ad hoc analytics. And right here across the board, you'll first notice that we have almost double every single one of these queries. I think there's one or two of them, maybe three of them that are just shy of 2x acceleration. So on average across the board, this is 4.6x acceleration, and as high as 7x or 6.6x for the top 10. So these are not applicable only to cherry-picked queries, even though Bigstream's approach is to focus on certain operators and those that we've identified as most prevalent in your average Spark job. This has wide applicability across different types, in this case of TPC-DS queries. Our customers actually see some of the biggest performance, not necessarily in the ad hoc analytics type of workloads, but in some of the ETL and ingest big data pipelines into a data lake, Delta Lake, data warehouse, where they really are facing SLAs, and we can help them meet those pretty impressively. This query, if you see in the note there, this is on JSON data with compression, and using three SmartSSDs in this cluster. Again, the acceleration is built operation by operation specific to a data format, and so we build up that library over time. So if this is so great and the results are so compelling, why doesn't everyone just throw on FPGAs and GPUs, SmartSSDs right in their Spark cluster if I'm a Spark user? Well, it's not that simple. And in fact, FPGA programming and GPU programming are pretty intricate. And the fact of the matter is, this audience, Data and AI Summit, the Spark user tends to live up at the top of this diagram, right? They're focused on making better ML, AI models, optimizing data pipelines. They would tend, and you would tend not to really want to worry about the plumbing, the underlying hardware and compute infrastructure, and vice versa. Those who spend their time building a data center or optimizing a public cloud environment aren't as close to the data platform. And so we describe this programming gap of these two different worlds that makes it difficult to incorporate really the best tool from a computing perspective into an environment like Spark. So that's where an organization and software like Bigstream come in, and where we've devoted the last 5 years to building expertise to make this seamless to the Spark user. You've heard me say it a couple times, but zero code change. I break up our innovation in these three buckets here on the right. But that first one, the main goal is to ensure that the Spark user doesn't have to think about this, doesn't have to change any of their Spark code or heavy configuration changes. And say in EMR, you can be up and running in minutes, adding Bigstream to your Spark clusters. This middle piece, again, I've touched on it, and we'll go a little deeper. Bigstream examines Spark's physical plan. Spark, other big data platforms all have a data flow they generate, and Bigstream, in an automatic fashion, evaluates each component, each operator, to determine which can benefit from the acceleration that comes from software or advanced compute that we've talked about, like a SmartSSD. Then the bottom piece really is the third category, which is the programming of the FPGA, the SmartSSD, even that C++ native language that we bring in for software-driven acceleration. So this is where we focus integrating them in for a seamless access to the hardware acceleration. So some organizations, so NVIDIA's making a lot of noise in acceleration themselves, obviously with a focus on GPU in the last 6 months or so with Rapids. They're integrated, so they'd kind of be the bottom two pieces together here. But this is getting a lot of attention in a lot of spaces, not just with Spark. So I'm going to talk a bit about the numbers on here. But other examples of big data acceleration are even Google's TPU, right? So that's them declaring that the CPU is not the best tool for their ML AI frameworks, and so they can actually justify building a dedicated chip, an ASIC, in the form of a TPU. Amazon announced late last year that it's integrating FPGAs into the Redshift data warehouse so that they can accelerate their own tool. Facebook has some internal pieces with ASICs as well. A couple other examples I have there on the bottom are Reniac, which does so with Cassandra, TigerGraph with graph databases pulling in FPGAs. And so to come back to the visual on the screen, this investment firm identifies accelerators, the hardware side of this, as becoming a $41 billion industry over the next 10 years, and actually exceeding the CPU sales and the $27 billion that would be in the lower right there, and driven heavily by this space, by data analytics, big data analytics, and artificial intelligence in particular. So we're seeing a lot of excitement here. Bigstream has put its emphasis on FPGAs and SmartSSDs and software acceleration based on our assessment of the longest running components of Spark and where we felt we can have the biggest impact. My colleague Roop Ganguly is giving a talk tomorrow, Thursday morning, here at the Data AI Summit, evaluating different approaches, GPUs, FPGAs in particular, and some of the pros and cons about those. So be sure to check that one out before you leave the show. I want to shift back over to how it works, right? This is a somewhat simple diagram of how Spark works without Bigstream. And I want to go through this to emphasize how we can deliver this seamlessly. We are not getting in there and mucking up Spark. So the Spark driver and those writing Spark code over on the left, ultimately that gets taken and Catalyst will generate a logical plan, or rather several, an unresolved, a resolved, optimized logical plan. Got that narrowed into one step. And then ultimately a physical plan that gets sent off as Java bytecode to a cluster of usually CPU nodes. Here's where Bigstream comes in and what the world looks like when Bigstream and a Xilinx FPGA or a Samsung Xilinx SmartSSD come into play. Bigstream will evaluate the physical plan through data flow analysis and generate a new enriched physical plan, looking at our hardware accelerator templates. And again, each task will evaluate, can this be accelerated with software acceleration? Can this be accelerated with hardware acceleration? And so pushes off to the cluster that now has these accelerators built in. So again, this does not touch the inner workings of Spark, and so it is a seamless execution. And going all the way back to the top, the innovation of each Spark version really is all the pieces that aren't in blue here. And again, so we take what Spark accomplishes and then send things off to the best compute approach for the right task. Just before I hand this back over to Song, I'm going to show the same view where the SmartSSD is profiled here. Just one last point I want to make on the SmartSSD in particular, at the storage layer. There will typically be multiple SmartSSDs in the cluster. And so the data will be partitioned across those. And so as it's running the computations on the SmartSSD, which offloads the CPU, it's doing so across the partition data set to really have that big impact on overall acceleration. So thanks for your time, and I'm going to hand it back over to Song to show how the SmartSSD really works in a Spark cluster.
Thanks, Steve. As mentioned earlier, let me introduce what SmartSSD is, and then how it operates, and then what kind of acceleration can be done. From the outside, it looks like just regular standard NVMe SSDs. And then inside, there's a 4 terabyte of Samsung VNAND, and then also it has an FPGA that can provide acceleration functions, and then 4 gigabyte of the DDR memory for FPGA to use. So next slide shows how that acceleration is processed. So x86 sends the data processing command to SmartSSD. FPGA reads data from the flash directly attached to the FPGA and then process it locally. Then only the process result returned back to x86. So this basically no CPU intervention is required. And then also the returned result is the data of interest only. This picture on the right shows the detail I just mentioned in the previous slide. The picture on the bottom shows how data pipeline can be designed with the acceleration functions such as decryption, decompression, parsing, and filter, and then aggregations. And we can create a customized data flow by stitching each functions in any order, the fashion. We are in the process of making SmartSSD available in the cloud. And then we also have partners who can provide turnkey solutions. For example, the Bigstream providing the Spark accelerations, CTXL providing video transcoding solution, LLL provides cyber security solutions. IDTCom can provides the data compression and decompression, and also some regex functions as part of that the acceleration solutions. This chart shows a SmartSSD technical spec, as mentioned before. It's a U.2 form factor of the SmartSSD, and then it comes with the PCI Gen 3x4 interface, and then 4 terabyte of enterprise class SmartSSD. Okay, I'd like to conclude our presentation with this brief total cost of ownership analysis. In order for us to calculate this TCO, we actually have done a lot of the additional calculation and then analysis and performance measurement. So the performance result used here is what Steve presented in the previous section. We are able to achieve around 4.3x acceleration with SmartSSD accelerations. So the tested configuration here is an Intel Platinum class processor CPU, and 3 SmartSSD per individual server. So in order for us to achieve 1,000 queries per hour, how much you have to spend with the CPU-only solution versus what is the CPU plus SmartSSD with the Bigstream acceleration is shown here. So you can see, you can save more than 60% of the TCO. And then this is the total cost of this ownership for 3 years. So this one can show you the key value of acceleration, how much savings you can make. So thank you for listening our presentation. If you have any additional questions, and then please reach out to us. Thank you.